Hello, I'm Roman. Welcome back to the series of the videos of building the convolutional neural networks from scratch. And it is based on the previous series that is called Neural Networks from Scratch in the Python, well, in the Golang, sorry, but I wrote all of the things in the Golang. So I used the book that is called Neural Networks from Scratch in the Python, but again, I wrote everything with the Golang and all the code is published. You can see it, and there is a published series. It's pretty big, around 72 videos. I finished it quite recently, 2 months ago, and right now I'm building the convolutional neural network. So I'm using various of the different articles to help me to go through this journey. And in the previous video, I kind of tried to brainstorm how I can structure the data. Well, how I can structure the data to fit the current implementation of the dense layer and how I implemented the model. Just to quickly show it, so I have the model and we have the train method, and the idea that in the train method, well, basically we have the model with the forward method, and the forward method is kind of simple. So it takes the input data and it passes it into the input layer, which is actually just the copying of the data, but it makes it easier to conform the input layer to the layers interface. And basically then what happens is by going through all of the layers that we have, and this is the layer interface. We're going through all of the layers and we taking the output from the previous one and passing it to the next one. And the trickiest part is that, for example, for the dense layers and for the activation function, it was more or less one-to-one relation between the input and the output. So for example, the input data is a two-dimensional array where every row represents a specific sample, and you can see that, for example, in the train methods, we have, for example, we can define number of the epochs. I think that should be better. We have the number of the epochs, plus within one epoch, we have a batch. So we're slicing the data based on the batch size. Based on the batch size. So for example, for the fashionist dataset that I'm trained before, so I made a category predictor just on the dense layers. It was 128. We can, I think, run question below here, so we can see that this is the batch size, and this is the batch size, and you can see, and again, so every row represents, as for example, the specific image. And for example, if we pass it through the dense layer, the transformed results from the image into the neurons will be, one-to-one relation. But with the convolutions, it's trickier, because if we take a look, that one convolutional layer could have several, well, it's called here filters, but it's actually the kernels. So it could have several kernels, and I think that the better representation is here. So for example, we have one input image that could result into several convolution operation, meaning that if I pass one image, the result will be 3 layers. Well, not 3 layers, 3 corresponding to the kernel outputs. And this is where my approach with layer interface kind of breaks, because it just returns the whole data kind of all at once. And what I tried to understand in the previous video is that what I can do and what is the way I can represent the data. The trickiest part, actually, if I want to have multiple convolutions one by one. So for example, I have a convolution, then the max pooling, and then I want to add another convolution. This thing actually makes it harder actually interesting with the fun. But what I decided, I mean, while I've been sleeping, and you know, I wanted to think about this after, and what I decided that I will actually go with the merged solution, and I will try actually to implement this architecture at first and fit it into my code structure. So I will have only one convolution and I will have only one max pooling. Then I could have many dense layers. It doesn't matter here actually. But this is what I'm going to do. So, and the way I want to approach this is the convolution will stack all of the convolutions results for each kernel into one row. So for example, I will have for the one input image, the output will contain, one row will contain, for example, with the 3 kernels, I will have 3 convolutions as the results. The only thing that I need to pass this information somehow to the max pooling. So in the max pooling, I can actually sub-slice this array and understand where is the data for the first convolution, for the second, and so on. So this is what I will start doing it today. So we have the initialization methods, and I think that the thing that I need to be able to pass into the max pooling is the output shape, well, more or less the size. So for this, I want to change the init method. For example, if for the input shape is what is the input shape? Wait. Where it's used? Not anywhere actually. I always can get number of the rows from the input data in the forward methods, but regarding, well, we define in the filter size and the filter number, right? And what I need from this is actually the output size. So the output, so that's going to be output size with the integer, and the output size we can calculate it already, right? So this is actually going to be the output size, and I think it's better to store its output size. We can store it and we can actually calculate it. So we have the n, which is the layer input dimensions. What is the input? Oh, actually, this is incorrect, because the input, we actually need to take the input shape. So because the input shape is the input shape will represent the side of an image, in this case. Filter size. So we have the filter size, right? So the S is actually the output size. Okay, so output size equal to S. And I think I can do this for the first time. Right, okay, so how do we define? So we have the layer, we have the input. Well, actually, we pass it. We have the input shape as integer. I think I need to comment make some comments so I won't forget. So the input shape is the what's called side of input image with the height. Then we have the filter size. Yeah, I don't like. Okay, I will rename it. It's not the filter size, it's size of kernel nodes site, right? And the filter number is the number of kernels that we pass in. So the output result will have the filter. No. The output size is the input shape minus filter size plus 1. That will define the output dimensions of it. So this, for example, I don't need it here, right? Okay, inputs each row is an image for the fashion is grayscale. Okay, so for the output, so we have, okay, let me do some cleanup. How we will define the output? Output sample count rows multiplied by, well, not multiplied by, every row is kernel, no, output size multiplied by the kernel, by output size once again, because it's as it's 2D array, multiplied by the filters number, which means that then I can, you know, extract it back. So here it will actually be different. Now for the, so I will actually, for I, so I have I count, okay, rows calls. I'm not sure that I need columns. I need rows. That will be the inputs dimensions, right? And then we go for the rows. Then we go for filter. We have filter number, right? Okay, and actually, yeah, this is not going to be like this. Filters. By the way, biases is not the, I think, the every output shape. We have the filter shape, this one. Interesting why we have the biases. Yeah, I thought the bias is adds in the end, so it's equal to the number of the convolutions, no? It looks like there is a difference. So there is an output shape. Okay, so interestingly that they're not used. I mean, why do they actually even edit? Okay, I'm not sure about the biases. We have initialized a few things here. First, dimension. The filters and biases, which is an NumPy array, hold the weights and biases for the convolutional. Okay, but do they actually use it? Okay, so it's used for in the backward method. Okay, this is completely different. And this is the dense layer and the backward path, but it's not used in the convolution. I mean, why they added it? Weird. Okay, but do we have it? Okay, I will need to find a better thing for the biases, because I thought that... Okay, we will get back to this later. Okay, but for now, what do we have? So the output is actually not an array. And actually I can do it here. Same should be with the inputs, right? As they go in pair, get the inputs, I can relate. That's the same. So it means that I have the output. No. So that should be, it's new. So how I would define the... So we're actually going to do this. So the number of the rows should be the same as from the input, because it represents the number of the input samples. For the columns, it's interesting because I'm going to have the number of the filters multiplied by the output size. So we have number of the filters, and then we have output size twice. And yes, we allocated the new memory. So what we're doing then right now? So we're going through the rows, we're going through the filters, right? So in the row, we actually need to take a slice or a sample. So we have the sample row, which should take inputs row view, right? Then we go through the filters number, and we need to, I think, calculate the results. Okay, but how the kernel output should be something like this, right? So we're using what's called the cross correlation between the sample and we have the kernel. And where we have the kernels, we have the kernel of, well, actually filter. And kernel output declare. This one variable. Okay, it's 2. Cannot use sample roll as the math dense value in arguments. Okay. Okay, so here I assume that it's two-dimensional, right? Okay, so I need actually to input 2D array of image, currently grayscale, and same for the kernel to the array, right? What it means? It means that here I need to reshape vector into two-dimensional array, which means that I need to have row view. Why do I have the date? This one. Then it means that I have the sample row then to the array. I'm writing it verbose so I can relate to this, which means that I have the new dense of size input shape, again layer input shape, and the data will be the sample row, right? Then it means that I can change it this one. Why you don't like it, kernel? Okay. Cannot use sample or variable. Oh, okay, so this is the reference type. I need to do this, right? Also, I need to take the error. If error is not equal to nil, I will do this for now. Oh, right. I'm still confusing the operands. Declare but not used. Nice. That means that I have the kernel output, and then I need to add it to I need to accumulate all of the things here. Wait, and the kernel output will be a 2D, right? So then I need, I guess I can do something like row this one and edit more. Okay, row outputs data. This is going to be, I will do float 64 0 because we'll use append, and then we have append row kernel output row matrix data. Can't use value as the flow. Really? I cannot. Okay. And why you don't like it? Oh, okay. That means that in the end I can output set row. And we have here and we have row output data. Okay, what it means? It means that in the end, we'll have the output with the same number of the rows as the input samples, and we will have the output that will contain all of the outputs after the convolution between the input data and the output. Okay, so it's input size, right? That's not filters, that should be kernels. And where else? Okay, filter size, that should be kernel input shape. Okay, kernel count. Return the output size, and what we have here, filter number, kernel count, output size, input date, input data. I still have question about biases. With the D inputs, I think we will allocate it during the backward path. But right now it kind of makes sense for the output and for the and for the inputs later. But we actually won't need. Well, we will need the D inputs when someday we'll have the chain convolutions. But right now it's actually won't be called because if we have model backwards. Yeah, it takes the loss. Yeah, so the last layer will use the previous D inputs, so the D inputs for this one we actually won't need conv backwards, right? Okay, that should work. I'm still confused with the biases because they're not used, but this is kind of what we have. Also, okay, so we have the relu activation function. So right now, let's take a look at how it works. So how it will work. So we have the input, we'll make a copy. The output will have the same shape, the same size of the as the input, and in terms of the convolution, it will be the several samples where every sample consists in one row, but for the convolution, the output of the convolution will have multiple kernels in the same output. But for the relu activation function, it doesn't make any sense to do the changes because it just looks at the value and returns everything that is bigger than 0. So that's fine. We definitely can use it. So now for the backward path. Well, for the backward path, this one is interesting. Create a random D. Okay, so then we're going to work on the activation. So we will have the D values, which in this case, D values comes from max pooling, right? No, actually, it will come from relu, but again, more or less it's the same. Well, via relu. What it means. So we will have the D inputs. I actually don't know if I need to grade it for now. The filters, we create a random. Okay, that's we will use the DL filters. I don't know. Okay, why do we return in it? Also, the inputs. Okay, but again, we are not going to actually use it. I don't need to. This is the filters. Okay, and what we're going to do actually for the backward pass, so we'll go through all of the filters. And what we going to do. Calculate the gradient of loss with respect to the inputs. But I'm not going to use it. The one, at least for the architecture that is presented here, I think the real one is only this one is actually used. Because it goes through all of the filters, it calculates the cross correlation between the input data actually again and DLD out. What is DLD out? Okay, so this and the input one again with the valid mode. So the max boolean actually should be the same, have the same structure, right? Where is the max boolean? Oh no. Okay, I think I need to actually implement the max boolean first properly, because do not involve gradient computation like other operations that require gradient calculation, such as convolution of full connected layers. Max boolean simply passes the maximum values to the next layer without any. But should it expand the size? Because the inputs and the size of the input data. Okay, so the input data in terms of the max boolean is the output from the convolution, which will have the same size. And during the forward method, it will shrink it, I mean reduce the size, and this is how it works. So we have the where is this one? This is how we decreasing it, but for the backward path, it actually takes the dimensions from the input data, and the input data is the output from the convolution, which is the result of the convolution, right? But how it will? Okay, so it goes through number of the channels, output height, output width. Okay. But what is the output? Okay, so this is the reduced one. Oh, so how? So it takes the loss from the input one. It takes its value that we go through, and then it assigns, well, multiplied by the mask, and it uses this range assignment. So for example, if it's 4 by 4, like for all of the 4 elements, this will be triggered with, with the mask. And mask is a patch equal to npmax patch. Okay, this one I actually need to debug because I'm not fully understand what it does. But okay, but looks like before going to the backward, I actually need to implement the max boolean layer, and that probably would make more sense. Okay, so I will start it a little bit and then we go next. Max boolean. Okay, max. Let's be consistent with the names. Package layer. Convolutional layer. Okay, max. Okay, type max boolean layer, right? And I think the only thing we actually have is the pool size. So I'm thinking, should it be public? Probably not. But in that case, I will need to have the initialize method. So, okay, let's make it full size. Int, right? And then what we actually do how the forwards. So here it's max pooling. We have the max pooling, right? What it means. We'll have the input data, and for this one, inputs comes from convolutional layer, and this is okay. So I actually will need, or maybe not. I need to know the kernel. I need to know the output size from convolutional layer and number of kernels from convolutional layer. Otherwise, I won't be able to do this. I won't be able to do this. Well, not this actually. I won't be able to do this. Because, okay, so here the input data actually represents one sample, but in my case, it's several samples. So I need to, extract it from the row. But I can assign it from outside, right? So we call it input size, and we should have the kernel count. In that case, I can go over the samples. And okay, so the output again will be the dense, but it's going to be a big one, right? So the output is going to be kind of the same. So rows corresponds to sample count. Calls contains from results of max pooling for all kernels. Right? But that means that I will need to have an actual array. Oh, basically, I'm going to allocate the output. So the output is going to be the interesting. Okay, so we actually have the rows from the input, right? We have the rows. Then for the number of the columns, we have the kernel count, right? But then we need to multiply. And this is what I actually need to calculate. So then I ignore this one, right? Input width, input heights. I assume again they all square. So the output size, it's the, again, input size divided by pool size. Output size twice and nil. And I guess I should have the output size. Output size int. Okay, so what we're going to do now? So we need to have a loop through kernel, which means that we have the kernel count. What happens? Right, and in order to do this, okay, so they manually. So then we actually have I, which is layer, and that's the input size, right? Or again, J, again, input size, right? We need to do the same. We need to have the start, end, and we need to create a slice. But what actually I can do? Oh, and then I need actually the input values. And this is why it's going to be, we have the inputs at, row view. We have the row view, which is the kernel I, and then we should have okay, I can do this, but then I guess I need to define the slicing. So I'm going to start from 0 multiplied by the kernel I, and then no. And then kernel I plus 1 multiplied by, yes, because it should be kernel like the index multiplied by the input size, and then we have plus 1 multiplied by the input size, and that's going to be the slice of the input values. Okay, and then we can actually go it through I and J, and then we can convert it into the dance, I think. In dance, it's new dance. That's going to be layer input size, and input values. Why I'm going to do this? Because it's going to be easier to do stuff like, I think I have input then I can do this. So we have the start, we have the K, which is I think I use it somewhere. Okay, it's plus. I plus layer whole size, right? And we have J plus layer whole size. So this is the slice. Oh, it's for the output. Okay. It's actually output. Okay, then starts I. Okay, you know what? I will continue this in the next video. It's already like a lot of the time. So I'm going to finish this one. Then I will do the same backward, well, for the backward paths, and that will give me more understanding how I should implement the backward for the convolution. I will cover it with the test, so it will be easier for me to understand what is actually happening and that I did not make any mistakes, because right now it's a lot of the kind of blind coding, and for sure I made some mistakes, but I will see it later. But and I still need to think about the biases, because I mean this article is a little bit weird, so I will take a look at another one. I think the biases should be the same as the number of the kernels, so we can add the bias into the outputs of convolution between the input and the kernel, and then we can add bias into this one. But this actually affects how I will implement the backward path. So I will dive a look into this one, but for now, thank you for watching and see you tomorrow. Bye bye.